Hello grade 11s, welcome to the lesson on rates of change. I hope you enjoy this and I hope this clears up any problems or any confusion you might have about rates of change. First of all, let's take a look at what we're going to be learning in this session. Just to remind you, we're going to do a quick summary on ratio, but we're going to be focusing more on rate, speed, distance and time, and other rates of change. Let's get into it. Let's have a look at ratio. First of all, the important thing with ratio is that it's used to describe the relationship between two or more quantities of the same type, which means that our quantities always have to have the same unit or the same measure. When I think about ratio, I think of oros, because on the bottle it always has something that says 1:4, or 1:5, or 1:6, but usually it's 1:4. What does this mean? For every 1 part of oros that you pour into your jug, you have to put in 4 equal parts of water. And it doesn't matter what units we use, as long as each of them are the same. So if we put in 1 liter of oros, we have to put in 4 liters of water. If we put in 1 cup of oros, we have to put in 4 cups of water. If we put in 1 jug of oros, we have to put in 4 jugs of water. Now, as I said before, it doesn't matter which quantities you use, as long as the quantities are of the same type or of the same unit. Think about it this way. If you put in too much oros, it's so sweet that you can't drink it. If you put in too much water, it's so bland that it tastes disgusting. That's why we have ratios. I'm sure all of you who do geography have become very familiar with this site, 1 in 50,000. And when we compare, remember that we have to have the same quantity or the same unit. So 1 centimeter on my map will be equal to 50,000 centimeters in real life. Or if I have 1 inch, which is a British measure, on my map, it'll be 50,000 inches in real life. So like I said before, it doesn't matter what the quantity is, as long as you compare the same quantity. Let's move on to rate, where we compare two different quantities. Let's have a look at the definition. A rate is similar to a ratio, but it compares two quantities with different units. The second quantity is often a measurement of time. So a rate often measures how quickly something happens. For example, take your oros and you pour it into a cup. You might want to measure how many cups per minute you can pour, right? We are measuring cups per minute, which is a measure of time. Let's think of another example. You're running a bath and you want to see how fast you can run your bath. When you open your tap, you might measure the rate of the tap in liters per, and we usually use our / minute. And this can lead to all sorts of questions like, how fast will my bath fill up if it's got a capacity of 100 liters? Well, we can say it fills up, our tap fills up at a rate of however many liters per minute. And that can give you an indication of how fast your bath can fill up. We can also use graphs to tell us what a rate can look like. And usually our graph will go up at a constant rate, which shows us that, let's take for example our bath example, our bath is filling up at a constant rate. the tap is flowing at a constant rate. It's going up at a constant rate. Let's have a look at our next one. Speed, distance, and time. Let's go through these bullet points one by one. The first one says, if the rate of change stays the same, i.e. constant, then the graph will be a straight line. So let's have a look what this graph would look like. If we have a graph that's rate of change is constant, our graph will be a straight line, just like that. If we have a constant rate of change, it means that over a period of time, our distance, or whatever else is changing, is going up by the same amount over each period of time. So think about it if you're in a car. If your car is going at 80 kilometers per hour and you're on a highway, your speed doesn't change. It means that for each unit of time, you're traveling the same distance, which means that your graph is constant and it'll go up in a straight line. For our second bullet point, if the rate of change varies or changes, it means that your rate of change isn't constant and your graph will be curved. Let's have a look at how this would look like. Let's draw our axes and over time and our distance. Think about if you stopped at a red robot and you suddenly accelerate after the light goes green. You will start off by traveling a small amount of distance over a given time. And the faster and faster you go, the more and more distance you will travel over a certain period of time. Let me make this a smooth graph. Can you see how that's a curved graph? In this amount of time over here, in this amount of time over here, you have traveled a small distance. Whereas in this amount of time over here, you have traveled a greater distance. This amount of time, you have traveled an even greater distance. So as the time increases and you get faster and faster and faster, the distance you cover will be bigger each time and your graph will be curved. And we can say that this is when our rate of change is not constant. In another way, we can also say that what happens if we are going very fast and suddenly we slow down? Well, this can also be represented by a curved graph, and we start off by covering a very big distance, and the distance that we cover per amount of time becomes smaller and smaller and smaller, and that's why our graph is curved upwards and not going up faster and faster. Let's just explain this once more. Over here, in this amount of time, you can see that we cover a very large distance, whereas in the next amount of time, the distance that we cover gets smaller, and in the next amount of time, the distance that we cover becomes even smaller until our graph becomes flat, which means that we aren't covering any more distance, which means that we've stopped. Right, let's go back and have a look at our next bullet point. If the rate of change is positive, the graph will be increasing. Let's have a look at a new graph. Let's draw our axes. And I'm going to draw another axis over here to compare the next thing. And like we said, let's go back to our bullet point. If the rate of change is positive, the graph will be increasing. So if we have a graph that is increasing, it means that our graph will be going up, and it is positive. Let's think of an example. Let's go back to our bath, filling the bath. If you turn your tap on, your water in your bath increases, your graph will be positive, and over your amount of time, the water in your bath will increase. But let's say you have a full bath, and there it is, you're sitting in your bath, it's absolutely full, and you pull your plug out. What will happen to your water? There will be less and less water over time, which will show that you have a negative graph. Your graph will be going down. And that is exactly what I was talking about over here. If the rate of change is negative, the graph will be decreasing. It'll be going down. A vertical line in a graph means that the independent variable stays the same as the dependent variable changes. So let's have an example of that. Let's draw a graph, and once again I'm going to draw two graphs so we can compare situations, and we get told if we have some sort of vertical line, it means that over here, in the matter of time, our dependent variable, which is always drawn on the vertical axis, changes, whereas time doesn't change at all. Let's think about something that could be represented like this. Let's go back to our bath example. If you get into the bath very suddenly, it takes a matter of a split second. Well, that's not like me, I get into the bath very slowly, but some people get straight into the bath and the water rises very high within a matter of seconds. So on our graph over here, our dependent variable has changed, whereas time hasn't really changed at all. In that split second that you get into the bath, the water level has gone up, but the time hasn't changed. Now let's look at our second scenario where we have a horizontal line. Actually, I'm going to change that. Let's say we've got a horizontal line. This means that our dependent variable does not change at all, whereas our time does change. Let's take, for example, a road trip. And over here, you're getting ready to go for your road trip. Your little brother's playing around, he can't find his iPod. Your little sister needs to get some water, and you're waiting in the car. Are you going anywhere? No, but time is definitely going somewhere. You're getting later and later and later. This can be represented by a horizontal line. You're not moving anywhere, but time is still running. And then all of a sudden, our line goes down, which means that you've started moving and your distance is now starting to change. Doesn't matter whether it's going up or down, but the point that I'm trying to illustrate is this horizontal line means that nothing is happening, but time is still marching on. Right, let's go back and see if we can spot this. A vertical line means that the independent variable stays the same as the dependent variable changes, right? We've got that. And over here, a horizontal line, you're waiting in the car, you're waiting for your brothers and sisters, they're not coming, and you are not moving anywhere. This means that the dependent variable stays the same, i.e. the distance, as the independent variable changes. So time is definitely marching on, but you're not going anywhere. Right, I hope these graphs have taught you something. Let's move on to an example and see if we can apply our knowledge. As part of soccer training, Sipho runs 10 kilometers in 1 hour. This means that he's running at a rate of 10 kilometers per hour. Look at the two graphs drawn below to compare his walking and his running rate? Well, here we've got a graph. On our bottom axis, we've got time, and on our vertical axis, we've got distance. Time is the independent variable, and what depends on time? His distance. If you have a small amount of time, he will have run a small distance. If you have a large amount of time, he will have run a longer distance. So let's have a look at this. Can you see that the slope of the graph shows how fast Sipho moves as time passes? In other words, it shows how fast he is covering a distance. I'm sure you've noticed that one of these lines represents his walking speed and the other line shows his running speed. Can you tell me which one it is? We're going to get there. The steeper slope represents Sipho's running speed, and the gentle slope represents him walking. Can you figure out why? Let's have a look at it. Obviously, for him to run 10 kilometers, if he does it in a smaller amount of time, it means that he's running. Whereas if Sipho walks 10 kilometers, he's going to be going much slower, and it means he'll take a longer time to complete the same distance. So this blue line shows Sipho's walking. When Sipho is walking, he uses much more time on the x-axis to cover the same distance on the y-axis than when he's running. The ratio of the two quantities, distance and time, is called the rate of change, and it measures the speed. In other words, speed is equal to distance divided by time, and let me write that out a little bit bigger. The way that I like to see it is in a fraction. Speed is equal to the distance covered divided by the amount of time that it takes to cover that distance. There's one very important thing that we need to remember when working out our speed. Often, you'll get given graphs which are like this. We've got distance on our vertical axis, and we've got time on our horizontal axis. Now, time can be measured in two different ways. It can be measured in hours, and it can be measured in minutes. Often, when we're talking about walking, we don't say, well, it took me 0.2 hours to walk to the shops. No, you say, it took me 15 minutes to walk to the shops. But speed, on the other hand, is often measured in kilometers per hour. So time is often measured in minutes, speed is measured in kilometers per hour, and we have to make sure that we get the right things when we're looking at our speed formula to make sure that we give the right unit and we calculate with the right measure of time. So let's have a look at this. If we get given a graph with our time in minutes and our distance in kilometers, and I'm going to do a very simple example. I'm going to say that we walk at a constant rate and it takes us 15 minutes to walk, and I don't have space here, so I'm going to write it in the inside, 2 kilometers. And we want to work out our speed in kilometers per hour. First of all, we're going to say speed is equal to distance divided by time. And we can fill in our distance, which is 2 kilometers, and we can fill in our time, which is 15 minutes. But if we say kilometers divided by minutes, we're going to get our answer in kilometers per minute. Now, sometimes that is acceptable, but most of the time, in an exam paper or a test, you'll be asked to give your answer in kilometers per hour. And we need to make sure that we can convert our answer from kilometers per minute into kilometers per hour. So first of all, let us get an answer in kilometers per minute. 2 divided by 15. Let's clear this. 2 divided by 15. And we get 0,13333. We'll keep that over here. 0,133 recurring. That isn't a very nice answer. In fact, it's very messy. And besides, who knows what 0,1333333 of a kilometer is? And how are you going to measure walking that per minute? It's much easier, and it's also convention to give a speed in kilometers per hour. Now, I hope you all know that there are 60 minutes in 1 hour. To get from minutes to hours, we always multiply by 60. And we can do the same with this answer. 0,133 recurring multiplied by 60. Let's see what we get. We've got it on the calculator. Multiply it by 60 and we get 8. And over here, our answer, now that we've multiplied by 60, is 8 kilometers per hour. And I've changed my mind. I don't think we're walking to the shops, we're jogging. Most people can jog at a rate of about between 7 and 8 kilometers per hour. Are we all clear on how to work out a speed and convert it from kilometers per minute to kilometers per hour? I hope so. Right, let's move on and have a look at other rates of change. There are many other rates of change that you'll encounter in your lives. Some of these examples are a reading rate. How many words can you read per minute? A typing rate. Now this is very important if you'd like to become a secretary or a personal assistant to a big boss. In your interview, you're going to be asked, well, how many words can you type per minute? Will you be able to take the minutes of a meeting if the bosses are talking really fast? Will you be able to type out a letter really quickly? So typing rate is quite an important rate in the everyday corporate world. Goal rate. How many goals can you score out of 10 attempts? Are you a soccer player? Do you like playing soccer? Well, if you have a really good goal rate, you might be the person picked for the team. Number of words per page in a textbook. Now, I find this quite an interesting rate. In a maths textbook, I don't think the number of words per page is going to be very high, because do numbers count as words? Not really. However, if you have an English textbook or a history textbook, your number of words per page is going to be quite high, so the rates are very different in that. Cost of a telephone call per minute. Now, I know most of you don't use telephones anymore because we're all on Mixit and BBM, but back in the day, the cost of a telephone call per minute was quite important. People used to go to a payphone, or when they got their Telkom account, they would work out, well, if it's 30 cents per minute and I spoke for 10 minutes, how much is my phone bill going to come to? Another rate that we get in everyday life, and you're going to encounter this when you get out of school, get a job, start earning money, you're going to have to pay taxes. And you pay different amount of taxes according to how much money you earn. The more money you earn, the more tax you're going to pay. So obviously, it's a positive rate. The more you earn, the more you pay. We're now going to have a look at question 1. As you can see, we've got a graph here, and the question states, the graph below shows Ricky's progress during a sponsored walk. Use the graph to answer the following questions. Let's have a look at our graph. It goes up in a straight line, which means that he's walking at a constant pace. And our first question says, what was the total distance of the sponsored walk? As you can see here on our graph, this indicates distance and this indicates time. We're looking at the distance, and in this case, we look at where the sponsored walk ends, draw a line down, and our distance is 20 kilometers. That was an easy one. Let's move on to the next question. How many minutes did it take Ricky to do the following? Well, first of all, reach point A. Let's have a look at point A on the graph. Over here, point A, and we need to look at our time, and our time was 40 minutes. How many minutes did it take Ricky to do the following? Cover 10 kilometers. Let's have a look at our graph. We're looking at 10 kilometers. We can draw a straight line up until it hits our graph, and then draw a line to the left to have a look at our time, and our time was 100 minutes. And for our third question, we are wondering how long it took Ricky to cover 15 kilometers. Let's go and have a look at our graph. Wow, we don't have 15 here. Well, 15 is halfway between 14 and 16. And obviously we are going to look at a time which is halfway in between 140 and 160, which is 150. And that is our answer, 150 minutes. Let's have a look at our next question. We're now looking at C. Calculate the time in hours that Ricky took to complete the entire race. Round off the answer to 1 decimal place. Well, we know that Ricky took 200 minutes to complete the race, but our question asks us to do it in hours. So 200 minutes divided by 60 to convert it to hours. And let's see what our calculator can do. 200 divided by 60, and we get 3,333. And we're asked to round the answer off to 1 decimal place over here. So 3,333 recurring, and we want to round it off to 1 decimal place. So it will be 3,3, and we always have to put in a unit, and our unit is hours. Right, let's move on to D. D asks us, determine Ricky's average walking speed in kilometers per minute. Use the formula average speed is equal to distance divided by time. Now we can choose any distance as long as we choose the corresponding time. I think I'm going to choose, well, 20 kilometers and 200 minutes. Right, our average speed is equal to distance. Our distance was 20 kilometers. And our time is 200 minutes. "20 kilometers divided by 200 minutes. Let's see what our calculator can do. And our answer is 0,1. And since we have to have a unit, we've been asked to work it out in kilometers per minute. And that is our answer, 0,1 kilometers per every minute that Ricky walks. Let's have a look at question E. Ricky completed the walk in 200 minutes. The winner completed the walk in 80% of Ricky's time. Calculate the time taken by the winner to complete the walk. Well, first of all, we need to say, well, what is 80% of 200? And of course, I'm sure you've learned before, how do we do a percentage? 80 over 100 times by the amount of minutes. Let's use our emulator. 80 over 100 multiplied by 200 minutes. And our answer is 160. So the winner completed the race in 160 minutes. Well, wasn't question 1 easy? Let's move on to something more difficult. Let's have a crack at question 2. Well, question 2 has got a graph, and it says, the graph below shows Greg and David's bicycle race of 50 kilometers. They were allowed to take only one 10-minute break during the entire race. Use the graph to answer the questions that follow. Well, here we have our graph, and as you can see, Greg is the blue line and David is the red line. And I'm sure you've figured out by now who's won, but let's have a look at the questions. How long did it take each boy to cover 30 kilometers? Well, let's have a look at our graph. Be sure not to get confused what lies on each axis. I'm sure a lot of you will have a look at 30 minutes and tell me what distance they did. That's not right. We're looking at how many minutes it took each boy to do 30 kilometers. So first of all, we have to find out where 30 kilometers is. And as you can see, we've got the 2 boys who did 30 kilometers in very different times. So let's start off with David, who did 30 kilometers the fastest. And as you can see, I've drawn a line until I hit David's graph, drop a line down, and as you can see, David did his 30 kilometers in 40 minutes. Now let's have a look at Greg. Greg took a little bit longer to do his 30 kilometers, and we draw a line all the way across until we reach Greg's graph, and as soon as we reach Greg's graph, drop a line down and have a look at the reading. It is 60 minutes, so Greg took 60 minutes to complete 30 kilometers. Are we all clear on that? Remember, don't get confused with your axes. Let's have a look at question B. Calculate the average speed in kilometers per hour for the first 20 minutes for both boys. Well, I think we're going to start off with David again. So let's just write here, David. And they said calculate the average speed for the first 20 minutes for both boys. So we're looking at our axes of time. And in 20 minutes, David is able to do 15 kilometers. So do you remember the formula for speed? Speed is equal to distance over time. Now we're going to have to fix things a little bit, but let's put in what we know. The distance that David did was 15 kilometers. And the amount of time that he did it in was 20 minutes. Now have a look at this equation that we've got here. If we say kilometers divided by minutes, our answer is going to be in kilometers per minute. But we actually want our answer in kilometers per hour. So I'm going to show you how to do that. First of all, let's take our calculator, and we want to say 15 divided by 20. 15 divided by 20. And our answer is 0.75. But our answer is in kilometers per minute, because our 2 values are in kilometers and minutes. Now we want to change our answer from kilometers per minute to kilometers per hour. And we all know that there are 60 minutes in 1 hour. So to get from minutes to hours, we have to multiply by 60. So we're going to say 0.75 multiplied by 60, and let's see what we get. 0.75 multiplied by 60, and what do we get? 45. So our answer is 45 kilometers, and we can now put it in per hour because we have changed from minutes to hours. Right, let's work out our average speed now for Greg. And we're going to do the same thing. Speed is equal to distance over time. And let's have a look how far Greg went in 20 minutes. Right, Greg, he managed to do 10 kilometers in 20 minutes. So his distance was 10 and his time was 20. And not to confuse us, let us put in our units, kilometers and minutes. Right, let's have a look on our calculator. 10 divided by 20, and we get 0,5. So his speed was 0,5 kilometers per minute. And we want to do the same thing that we did earlier, convert it from kilometers per minute into kilometers per hour, and we do that by multiplying by 60. Pop it into our calculator and let's see what we get. And our answer is 30. And that will be 30 kilometers per hour. Are we all clear with that? Let's move on to the next question. Our next question asks, who was the fastest during the first 20 minutes? Well, that's an easy one. We can refer back to our previous question and just look for the highest rate in kilometers per hour, or we can look at our graph. Who has gone the furthest in the first 20 minutes? Well, you'll find that over here, our red line, David, he's gone the furthest in 20 minutes, and as you remember in our last question, he went at 45 kilometers per hour, which was faster than Greg's 30 kilometers per hour. So who was the fastest? It was David. Let's move on to the next question. Question D. If the race started at 7:40 a.m., at what time did Greg take a break? Well, first of all, let's see when Greg took a break. And as you can see over here, this flat part over there shows that he wasn't moving. So that is obviously when Greg took a break. And his break started at 30 minutes into the race. So what we need to do is we need to say, well, 7:40 plus 30 minutes. We can't really do this on a calculator because, well, if you say 7:40 plus 30, you'll get 7:70, which isn't really an acceptable time format. So you're going to have to think about this a little bit in your head. What will be half an hour after 7:40? And our answer is 8:10. And for good measure, say AM. Otherwise, you might get confused and think that he's been riding the whole entire day. Are we all clear on that? I hope so. Let's move on to the next question. E. How many minutes did David take to finish the race? Well, let's have a look at David. Here he is. He's the red line. And in the beginning, it looked like he was going faster, but he actually ended up being slower towards the end. And over here, that's where he finishes, because we know that our race was 50 kilometers long. And let's draw a line down. And over there, it is 90 minutes. So David took 90 minutes to finish the race. That's a just easy bit of reading off the graph. Let's move on to the next question. Who was faster towards the end of the race? Well, we don't have to do any calculations of any sort. You could do an average speed and work out who actually was faster. But just by looking at the graph, we'll be able to tell who was faster. And if you look at the graph, over here in our blue line is Greg, and our line becomes very steep, whereas David's line flattens out a bit and becomes more shallow, which means that Greg over here was going faster. His rate increased, which is shown by a steeper line. So, who was faster towards the end of the race? It was Greg. Let's move on to the next question. And it says over here, who won the race? I think that's pretty easy to see. As you can see over here on our graph, the person who won the race would be the person who reached 50 kilometers first, and it was Greg. I hope you got a medal for coming first. Well, I think question 1 and 2 are quite simple. Let's move on to something a little bit harder. Have you ever been overseas or to a different country? What happens when you want to buy something there? You have to use the other country's currency. Well, an exchange rate is a perfect example of how we can use rates in everyday life. So let's have a look at question 3. Neo is planning a trip to Botswana. Before the trip, she visits a money exchange to buy Botswana pula currency. The following exchange rate board was displayed. Now let's have a look over here. Obviously, the exchange place was in South Africa, and they were advertising to buy and sell different currencies: the pound, the pula, the euro, and the lilangeni from Swaziland. And over here it says we buy and we sell. What on earth does this mean? Well, the we buy rate is the exchange rate at which Mr. Money will buy foreign currency from a customer. So if I had to go to Mr. Money with euros, this is the rate at which they would buy euros from me. Whereas if I went to the exchange company, Mr. Money, with my rands, these are the rates at which they'd sell me different currencies. The reason it's a little bit different is so that Mr. Money can actually make a little bit of money. But they make a little bit of money in a different way too. Let's have a look at this. Mr. Money provides the following example of how commission fees are calculated on currency exchange transactions. So, as well as buying and selling for a different rate, Mr. Money also charges commission. They charge commission at 1.7% of the rand value being exchanged, but if you exchange a very small amount, 1.7% isn't going to be very much, so they have made sure that they get a minimum fee of 45 rand. So no matter the amount of money that you exchange, they will get at least 45 rand, and if you exchange a very large amount of money, it'll be a lot more because there's no maximum fee. You will always be having to pay 1.7% of your money in commission. And they give us an example here. It says, say you would like to exchange 10,000 rand into British pounds. The commission fee is 1.7%. So over here we've got 1.7%, and to work this out, we say 1.7% times 10,000 rand, and in commission you would have to pay them 170 rand. And this is the fee that they charge for changing the money. Let's make sure that they got that right, and we'd like to say 1.7 divide by 100 to get it into a percentage, which is 17 over 1,000, or 1.7 over 100, whichever way you'd like to do it, and multiply it by our value of 10,000 rand, and we get 170. So that's correct. Let's have a look at question A. Use the exchange rate board above to show that Naya will receive, and this P over here stands for pula, 2012 pula and 30 cents, if she exchanges 2,500 rand into Botswana pula, and a commission fee is charged on the exchange. Well, how on earth are we going to start this question? First of all, we need to work out the commission fee, don't we? And our commission fee is 1.7%, and it's 1.7% of 2,500 Rand. Let's work it out. 1.7, and we turn it into a percentage by dividing by 100, and it is 1.7% of 2,500 equals. Change it into rands. Ooh, 42.5 Rand. Or if we read it out in rands, 42 Rand 50. But in our board over here, it says that the minimum fee is 45 Rand. So 42 Rand is less than 45. So we are going to say, well, actually, Mr. Money is going to charge us 45 Rand. We now say, well, here's our 2,500 Rand, and they're taking away 45 Rand as a commission. What's 2,500 minus 45? It is 2,455 Rand. We are now going to use this value to work out how many pulas we get. So if we'd like to exchange 2,455 Rand into pula, we're going to have to go back to our exchange rate board, and we need to work out, are we buying or are we selling? Well, it's clear that we are selling, because we have to look at this column over here, and we can look back at the exchange rate board, and it says we sell rate, the exchange rate at which Mr. Money will sell foreign currency to a customer. And we're looking at the Botswana pula, which is 1.22. So let's go back down to our amount, and we've got 2,455. We divide by 1.22, and let us have a look what we've got. 2,455 divided by 1.22 equals, and let's change that, 2012.295, and we can round this up to 30. So let's put this in over here, and we've changed it into pula, 2012.30, and let's see if that's the answer that we were wanting to get. And we've done it. 2012 and 30 cents of Botswana pula. We've done it. Let's move on to B. The graph below, as you can see here, shows how the commission fee on a currency exchange transaction will increase as the amount of currency being exchanged increases. So let's have a look at our heading, commission fees on currency exchange transactions at Mr. Money. And over here on our vertical axis, we've got our commission fee in Rand. And on our horizontal axis at the bottom, we've got the amount of Rand being exchanged. And let's have a look carefully at this graph. It starts off by being flat, and then at point C, it suddenly starts increasing. Let's see what the question asks. Part A is the horizontal portion of the graph. Explain why part A is the horizontal line. Well, I think it's got something to do with this value over here, and this value over here is 45. Let's go up and see if we can find something to do with 45. As you can see, the commission fee shows that there's always going to be a minimum fee of 45 Rand. No matter how little money you transact, you'll always have to pay 45 Rand until 1.7% of your value becomes more than 45 Rand. So I'm not too sure what you would like to say, but I would say something like 45 Rand is the minimum fee on commission, and it will stay constant no matter how little money you exchange until at C, 45 Rand is actually less than your 1.7%. So we know that at about 2,800 Rand, or just a little bit less than that, well, 1.7% of 2,800 Rand becomes more than 45 Rand. So part A is horizontal because that's the minimum fee. 1.7% is less than 45 Rand, but because 45 Rand is our minimum fee, we'll always have to be paying 45 Rand. That's our horizontal part. And now for the last question in question 3. We're back at our graph of commission, and it says, use any calculation to determine the maximum exchange rate on which a commission fee of 45 Rand will be charged. Give your answer to the nearest 10 Rand. Well, what we want to do is we want to find out basically this value over here. What is the largest amount of money that we can change and our commission will still be 45 Rand? Well, one way to do it is to say our amount, and we're referring to this amount over here. And if we have a look at our graph, well, let me just undo that. It's going to be quite close to 2,600. So we want an amount whereby if we multiply our amount by 1.7%, we'll get 45 Rand, or anything less than 45 Rand. But we want our maximum value, so we want our amount times 1.7% to be equal to 45 Rand. Now, in order to solve this question, we're solving for our amount. And to be more accurate, let's just say A times 1.7% is equal to 45 Rand. Now, to counteract this multiply by 1.7%, we are going to divide. So if we divide by 1.7% on this side, it'll cancel and we'll be left with A. But what we do to the one side, we have to do to the other side. So I'm going to say 45 Rand divided by 1.7%. Are we clear on that? Let's pop it into the calculator and see what we do. Don't forget that we have to change this 1.7% into a decimal. And how do we do that? We say 1.7 divided by 100. So here we have 45 Rand, and we are going to divide it by 1.7%, which is 1.7 divided by 100, and we get 2,647.05 with a whole lot of other numbers after our dot. And in our question, it said, round, give your answer to the nearest 10 Rand. And there'll be a mark in that, so you have to make sure that you say 2,647, what's our nearest 10 to that? And let's just write our answer as we got it, 2,647.06 with a whole lot of decimal places. But since we need to round it to the nearest 10 Rand, we will get 2,650 Rand. Shall we move on to question 4? Question 4 is a bit of a different question. It's all about getting in and out of the bath, which I'm sure you'd love to do at this point in time, but we've got a bit more learning to do. So let's have a look at question 4. Nancy decides to take a bath. The graph below shows how the water level in the bath changes over time. Study the graph and then use it to answer the questions that follow. Now let's have a look at this graph carefully. On our vertical axis, we've got water depth. All right, so you know what this means. When you fill up the bath, the water gets deeper and deeper and deeper as the bath fills up. And when you pull out the plug, the water will get more and more shallow as the water goes out. And then over here on our bottom axis, we've got the time in minutes. So we can tell exactly how long it took for Nancy to fill the bath up, for her to sit in the bath, and for the plug to be pulled and the bath to be emptied. So first of all, it asks us, How long did it take for Nancy to fill the bath? And let's go back to our graph, and when we turn the tap on, we can assume that we've got a constant rate of water flowing into our bath. That is why our line over here is straight, because we have a constant flow of water into our bath. And my guess would be that that is when the bath is full, from this point where she starts to A. And it asked us for how long it took her to fill the bath, and our answer is 5 minutes. Then it says, what do you think is happening between A and B? Well, A and B is this little section over here. And because it's a flat line, it means that, well, nothing is happening. The bath isn't getting more full. The bath isn't emptying. And I think you can be creative in your questions. Maybe she is waiting for the bath to cool down a bit. Maybe she is getting ready to get in the bath, because you can't get into the bath fully clothed. Maybe somebody phoned her and she needed to take a phone call before she got into the bath. So you could say here, she's waiting, or she's getting ready, she's on the phone, anything. As long as your reason shows that you understand that in this time over here, no water is going into the bath and no water is going out of the bath. And this happened between 5 and, well, a little bit before 10, so I would say 8, and this would be 3 minutes. So she didn't do anything for 3 minutes. Let's have a look at C. What do you think is happening between B and C? Well, let's go back to our graph and have a look. Here's B and here's C. Suddenly, the bath goes from 10 centimeters in depth all the way to 20 centimeters in depth. And it happened almost instantaneously, because this line is absolutely vertical. So what happens when you get into the bath? As soon as you get into the bath, you're displacing some water, so the depth in the bath goes up, and it goes up absolutely instantly as you get into the bath. So you need to say over here, what happens between B and C, and you can say here, Nancy got into the bath. Now, if you said Nancy put all her toys into the bath, or Nancy put her rubber duck into the bath, or Nancy threw her soap into the bath, that could be correct, but I don't think that toys or a rubber duck would be big enough to displace such a large amount of water, so it must be a human being getting into the bath. Next question. How long was Nancy in the bath? Well, this is a bit of a tricky question, and this has got to do with the next question as well. Most people would say that Nancy was in the bath between C and D, which is 8 minutes to, let's draw a line down here, 20 minutes. So I think most people would say, well, Nancy's in the bath between 8 and 20 minutes, which gives us a time of about 12 minutes. But we need to do a bit of detective work here. If Nancy had gotten out of the bath, we would have had a sharp decrease, wouldn't we? With her body getting out of the bath, the water would have suddenly dropped like it did over here in the first place. But it doesn't do that, does it? The water goes down slowly, which means she must have pulled out the plug and she was still in the bath. So Nancy over here was in the bath for 12 minutes, and then she let the plug out, and she was in the bath as it was emptying for a further between 20 and 30 minutes, which is 10 minutes. So I would say that Nancy was in the bath for 12 minutes while it was full, and another 10 minutes while it was getting empty, which is a total of 22 minutes. And by doing that piece of detective work, we can already answer the last question E. Did Nancy get out of the bath before letting the water out? Explain your answer. And you would say here, no, she didn't. And your reason being, there is no sudden drop in water depth. If there was a sudden drop in water depth, just like there was a sudden rise in water depth when she got in, we would know that she got out of the bath and then let it out. So if she had to have gotten out of the bath before she let the water out, we would have a sudden drop and then a rate at which the bath water would be let out slowly, like so. But there's no sudden drop. There's just a gradual drop over here, indicated by this line over there, which means that she let the bath water out while she was still in the bath, and the water went out gradually. I'm now going to be going through a couple of questions. I'm not going to give you the answers because that would be giving away too much, but I'm just going to go through some of these questions, and we're going to see if we can get a bit of help in how to solve them. So our first question in our exercise questions is this one. It's another graph, and this time we're looking at some trains. The graph below shows the distance travelled from East London by two trains, travelling in opposite directions. The train drivers for both trains come on duty at 6:30 a.m. and use 1 minute to warm up the diesel engines, and then they are both off at 6:31 a.m. They pass each other after exactly 6.8 minutes. Now let's have a look at the graph. Train 1 travels from Cambridge, which is a little bit of a distance away from East London, all the way to East London. And train 2 travels from East London, and it travels away from East London to Mdatsane. So if we have a look at this graph, it shows graph showing distance travelled, and it should be here from East London. I'm afraid you're going to have to pretend that that says east. And if you have a look over here, we aren't looking at the distance travelled by each train, because if we looked at the distance travelled by each train, we'd have an increasing graph on both trains, because the distance travelled would be greater and greater through the day. We're looking at something which is slightly different. It's the distance travelled from East London, or the distance away from East London. So as you can see, Cambridge is 15 kilometres away from East London, and the line goes down, which means that it is travelling towards East London. The distance between East London is getting less and less over time, which means it's getting closer and closer and closer to East London. Whereas train 2, as you can see, goes away from East London. It's a graph which is going up, which means the distance from East London gets bigger and bigger and bigger as the train gets further and further and further away. And as you know, these little flat lines over here mean that the train isn't going anywhere. For that period of time, the train is absolutely stationary. And you can guess what you want to, but I would say that it's probably for a stop or to refuel or anything that makes sense like that. And over here, our first question asks, what distance does train 1 travel between Cambridge and East London? And obviously, you are going to work out the distance between Cambridge and East London, and you'll be looking at your distance axis to work that out. Our next question, B, asks, what distance does train 2 travel between Dawn and Frere? And obviously you're going to look at your distance over here between Dawn and Frere, and you're going to work out the distance using this axis over here to find the distance between Dawn and Frere. Let's have a look at our next question. And it says here, if both trains leave at 6:31 in the morning, at what time will they pass each other? Write the exact time by giving the hour, the minute, and the seconds. So this is a bit of a complicated question because you need to go back and do a little bit of figuring out. We get told that we leave at 6:31 in the morning and that they pass each other after exactly 6,8 minutes. Now our first step would be to convert 6,8 into minutes and seconds, right? So we know that 6,8 minutes is equal to 6 minutes plus 0,8, which is a portion of a minute. And we're going to have to convert this part, our decimal part, into seconds because we've been asked to give our answer in hour, minute, and seconds. So how do we convert minutes into seconds? Well, 0,8 and, oops, let me get rid of my equal sign. 0,8 and we have to multiply it by 60 to get our answer in seconds. I'll leave that for you to do. And afterwards, of course, once we've got our minutes and we've got our seconds, all we have to do is say, well, the time that they left is 31 minutes past 6 in the morning, a.m., and we're going to add 6 minutes, and then we are going to add our amount of seconds, and you'll be able to give the exact amount of time, or the exact time that the two trains cross. Let's have a look at our next question. D. Why do you think train 2 stops at Frere and Dawn? Well, this one is for your own interpretation, and I'm sure you're going to come up with lots of very creative answers. You might say to refuel, for passengers to get on and off, or you never know. The train might not even be a passenger train, it might be a train for freight, in which case the stops might be to load goods onto the train. But whatever the answer is, I'm sure you'll figure out a very good reason for the trains to stop. This one's for your own interpretation. Let's have a look at the next question. How far does train 2 travel in total? Well, this is another easy one to read off the graph, and make sure you're looking at the right line, and it says how far does train 2 travel in total, and by saying how far, I'm sure that they are asking for a distance. So if you will be able to have a look at the distance and tell me how far, at the end of the day, does train 2 travel? Let's have a look at the next one. F. How many minutes does it take for train 2 to travel from East London to Dawn? So first of all, we're looking at train 2. Make sure that you look at the right line. And then it says how many minutes. Are you going to give me an answer in kilometers when they say how many minutes? Of course not. You need to see, well, from East London, we've started at 0 minutes. When the train gets to Dawn, drop a line down, see how many minutes it took, and obviously you're going to be looking on your horizontal axis, and so obviously you're going to be able to tell me in time how long it took to travel from East London to Dawn. Let's have a look at the next one. Our next one says, calculate the average speed of train 2. So once again, we're looking at this line over here, train 2, in kilometers per hour. Leave your answer as a whole number. Now we're very lucky because we've been given the following formula. The average speed is equal to the distance traveled divided by the time it takes to travel. So in train 2, we're going to look at our distance, at the very end of the day, what distance did train 2 travel? And we can use that as our distance. And secondly, divide by the amount of time that it took. Now you'll notice that time in this question is in minutes. But you've been asked in the question to give your answer in kilometers per hour. So we're going to have to fiddle our answer a bit, because if we just give a distance divided by time in minutes, and you'll get your answer with the unit of kilometers per minute. Now, you aren't going to get your full marks if you're going to give me an answer in kilometers per minute, because the question asked for kilometers per hour. Do you remember how to convert from kilometers per minute to kilometers per hour? Well, we know that there's 60 minutes in 1 hour. So to convert from kilometers per minute to kilometers per hour, we have to multiply our answer by 60, and we'll be able to get our answer in kilometers per hour. Don't forget, that's a very handy trick to know. Let's move on to question 2. Question 2 talks about a mother who's constantly driving her kids around. As you can see here, Mrs. Khumalo has 2 children, Mpho and Tumi. They attend 2 different schools. The following information describes Mrs. Khumalo's routine on one particular morning. She drives Mpho, who's 7 years old, and Tumi, who's 17 years old, to their respective schools. First, she drops Mpho at point A. Then, she takes Tumi to her school at point B, and then she returns home. Have a look at this following graph and see if you can see the corresponding points. We have A, we have B, and then when we get down over here, Mrs. Khumalo is back home. Let's have a look at the question. How long was Mrs. Khumalo away from home? This word over here, long, implies that we are talking about time, which means we are going to be having to look at this axis over there. How long was Mrs. Khumalo away from home? Calculate the amount of time that she's away. Let's have a look at the next question, B. How far is it from the Khumalo home to Mpho's school at point A? Well, if we look at the word far, it implies that we are looking for a distance, which means we are going to be looking at the vertical axis. How far away is the school, is point A, the school, away from home? And if we have a look at our heading over here, we need to make sure that we realize that this graph shows the distance traveled away from home, and that is Mrs. Khumalo's home. It doesn't mean the distance traveled overall, because can you ever travel a negative distance? No. But when we look at this graph where it says distance traveled away from home, if this over here is home, we can see that she travels further and further away, and then when the graph starts going down, it means she's coming closer and closer back to home. So if we look at B, how far away is it to Mpho's school? We can just calculate our distance, and I'm sure you'll be able to work that out very easily. Let's look at the next one. C. How long did it take to reach Mpho's school? And let's remind ourselves that Mpho's school is at point A, and how long means that we are looking at time. So once again, we're going to look at the horizontal axis, which is time, and you're going to tell me how long it takes to get to point A. Next, D. How far is Tumi's school at point B from home? Well, once again, how far means that we're going to be looking at distance. And if you look at our graph, distance is over here on the vertical axis, and you need to tell me at what distance does the car with Tumi in it, well, they've already dropped Mpho off, how far away is it from home? And let's look at the next one. E. How much time did Mrs. Khumalo spend at Tumi's school? Well, let's remind ourselves, Tumi's school is at point B on the map, and let's have a look here. Mrs. Khumalo arrived at point B, and then the line was flat. This flat line means that she didn't move anywhere. So you can make up any scenario that you want. Maybe Mrs. Khumalo had to go in and see a teacher, or she had, there was a lot of traffic at the school and she couldn't move anywhere, or any other reason. But the fact of the matter is that Mrs. Khumalo stays at the school for some amount of time. And if we look at this time, you can work out how long she stayed in that one place for. For our next question, F, we are going to calculate Mrs. Khumalo's average speed in kilometers per hour during the trip from home, and this is where home is, to Mpho's school. Do we remember that Mpho's school is at point A? So let's go back to our graph over here and let's see. We want to calculate average speed between home, which is at 0 kilometers away from home, or all the way to Mpho's school, which is, as we can see, 10 kilometers away from home. Do you remember the average distance formula? Average speed formula? Let's write it down so you remember. Average speed is equal to distance over time. Now, once again, we have to remember that we've been asked to give our answer in kilometers per hour, but our time has been given in minutes. I hope you remember from our previous example that once we work out the speed in kilometers per minute, we then have to multiply by 60 because there are 60 minutes in 1 hour. And only after we multiply by 60, our answer is in kilometers per hour. That's very important to remember. And there are many questions like this where you get given time in minutes, but you get asked for a speed in kilometers per hour. So don't ever forget that there are 60 minutes in 1 hour. I hope you understood that. If not, rewind and play it again until you do understand. Let's look at our next question. G. This is another average speed question. Calculate Mrs. Khumalo's average speed in kilometers per hour from Tumi's school back home. So let's have a look at our graph again. Don't forget that Tumi's school is at point B, and over here, this is where she leaves Tumi's school and starts going home. So you will first of all need to work out the distance that she travels back home by using the distance side, the distance axis. You will then need to work out how much time she takes to drive back home. And then we're going to put everything into our formula. Average speed is equal to distance divided by time. Now, once again, you have to make sure that you convert your time or you convert your speed into kilometers per hour, because at this point in time, your time is given to you in minutes, which will give you an answer of kilometers per minute when you do this calculation. But do you want your answer in kilometers per minute? No, You don't want your answer in kilometers per minute, you want your answer in kilometers per hour, and since there are 60 minutes in an hour, you multiply by 60 to get your answer in kilometers per hour. Well, grade 11s, we've gone through an explanation of rates of change, we've done some examples, and I've gone through the exercise questions with you. I hope this has helped, and remember, you have to go home and redo these questions to make sure that you understand everything. Good luck for your exams.